I'm Cyrus from Liberty, doing this work under Strasser, who you already heard of. This is just some work I've been doing on ferromagnetic colloids. So first, I'm going to give you a roadmap what we're actually going to be talking about today. I'm going to be going over the problem, what this research is actually trying to address. I'm going over the scope of this research in particular, my objectives, some of the equations that we're looking at and discussing, the formulation of those, some of the current results in both literature and what we are getting, and then some next steps for this research. So first of all, the problem. Why are we actually talking about ferromagnetic colloids? Over the past few years, ferrofluids have been researched and have shown great promise for targeted drug delivery. So that's one field that has influenced this research. And this has generated a lot of research across, the past 10-ish years on the dynamics of ferrofluids. And this, of course, has generated different models for ferrofluids and has displayed the vast potential for these types of fluids, not only in biomed applications, then also in other capacities like industry mixing or nanorobotics are two other main big ones. So with this research has come a few predominant models, as I said, implementing different numerical techniques and equations. So these typically focus on a few major parameters like magnetic frequency, magnetic amplitude, actual dimensions of the rollers or particles in these ferrofluids, and then the density of these particles within your specific fluid. The scope of this research in particular, we went to identify the major models being used in literature and the mechanics of these models. The two primary ones that I'm going to talk about are Ginsburg-Landau and Langevin dynamics. We want to use this to program a 2D model to test variables within a program like Python, simplify the dynamics of the models that we observed, and then observe the sensitivity of different coefficients and parameters within these models. And all of this we want to validate against a CFD model with an ANSYS fluent. The objectives of this research, we want to establish different behaviors for an MHD model, which is what this is, which we already heard a little bit about, which is able to analyze the following parameters. Frequency, so we want to really observe unique periodic behaviors within these fluids. The amplitude, we don't want to observe very low magnetic effects, but high amplitude, high AC current. Particle density, so we want to observe effects like drag and active matter, so the movement of these induced by these particles within the host fluid. And then the particle size, so how this actually increases or reduces the vorticity and the overall advection. So why are we doing numerical? Why can't we observe some type of analytical or semi-analytical results within these types of fluids, within these types of behaviors? Maybe just present an initial correlation. It won't be exact, but why couldn't we do that? Well, first of all, it is very transient behavior. We have vortices, we've got periodic and irregular densities. Second, for MHD, analytical and semi-analytical methods can only be used if you have a very low amplitude and low frequency behavior, basically treating it as a constant within your model, which is not ideal and not what we want to look at. So what are these equations that we're looking at? MHD traditionally stood for coupling Navier-Stokes or some form of fluid equations with the Maxwell equations. Now, if you want to model a 2D simplified version of this, there's many options that go outside of just Navier-Stokes and the Maxwell equations. One of these is Langevin dynamics. That's a very popular model nowadays for these types of problems. And then another one, which will be the main focus of this research, pairs the fluid equations with concepts from Ginsburg-Landau theory. So first, I'm just going to go over the Langevin dynamics equations fairly quickly, just to give an overview of the other major equations used with this type of research. So this is specialized LD for these types of problems. One such as Vesick's model, a very popular model for active matter, and is very, very good. Langevin dynamics is very good for particle interactions. That's kind of what it's known for. It has a few major equations. One is dipole interaction, which you can see here, and then equations for motion, which here you can see one version, which is translational and rotational motion. The terms I outlined are random fluctuations, Brownian motion, noise, and this is iconic for these different types of models. Makes them very applicable to this type of research. And if you want to see this, I have a source at the end. The other approach, Ginsburg-Landau, It's very good for frequency analysis. That's why it was introduced, and that's kind of where this comes into our research. It has three major equations for our model. One is coarse-grained translational velocity. This is for the particles within this model, and you can see it here. Another one is a 2D depth average Navier-Stokes, which is for the fluid in particular. You can see this here. And then the magnetic moment density, so how it's actually being forced with magnetic forcing. See this here. And the coefficients outlined red are these coefficients taken from GL theory. So that's very important. If you'd like to see that, I have a source at the end too. So why would we choose this GL model over Langevin dynamics? Well, there's a few pros. And one is that it does emphasize frequency, which is what we want to observe, over frequency and periodic behaviors over just particle interactions. But that's also, it also presents a more accurate behavior of the colloid as a system. It has an equation for both the particles and the fluid, which is not something that LD represents. The cons are that it does not capture individual particle dynamics like LD does. And it's not widely used as LD has been for this type of research. But one question that we could ask is, what do these GL results look like in previous literature? So one such example of this showed a very steady relationship between the frequency and the density, which I thought was extremely interesting. You can see that here. State one in this demonstration is trivial, so you basically have no motion. State two, you can start to see bands forming. This is around 20 hertz. State three, you can start to see steady fluctuations. But then in state four, you actually see vortices forming. And you can see here in this video, this is state three, state two, and then state four. And this are all plots of normalized density. And you can see this is very transient behavior, but you can see steady patterns coming out. So this is quasi-steady state. So our attempt for this model, we want to simplify the model I showed you with the 3 PDEs, make the coefficients manual variables, and then we want to run a sensitivity analysis, fine-tune the model, see where the coefficients and terms are most valuable for the simulation, kind of where this behavior takes place. And then once this simplified model is established, we want to shift gears, implement a full 3 PDEs, all the coefficients and everything like the model I showed you before, and then compare this against a simplified ANSYS fluent simulation to test overall validity. So how is our attempt different from the results I just showed you? So we want to observe and quantify the following behaviors specifically. Advection, we really want to look at active matter, particle dynamics in terms of drag, and clustering behaviors. And these behaviors were studied in previous literature, but they were not the exact focus, and they were not exactly quantifiable. They didn't give quantifiable results. So that's one thing that we want to look into. So in terms of our simplified idea, we want to just take 2 PDEs from the previous model, which is the particle and fluid dynamics here. And then we want to just replace the magnetic moment density, which is a magnetic forcing term within the particle dynamics, which you can see here. And then we want to simplify the 2 parameters terms in the Navier-Stokes equation. You can see make those constants a variable. And you can see that this is drag coupling, which will lead to advection. So these terms are very important for this model and ones that we want to look at. In terms of our results, to implement this model, we have a fully periodic domain, a first order upwind. This was primarily implemented for stability because we experienced a very unstable model. Our main output parameters that we were looking at were the particle velocity, vorticity, and the density of these models. And we found that fine-tuning was very, very much a hit or miss. If the parameters were changed to something non-trivial, so where we have magnetic forcing above 0, then the solver would implode very, very soon after it was started. We wouldn't be able to get a good data set. The magnetic forcing was not inducing periodic behavior, which is probably just, it wasn't able to run for long enough. So that is also a problem that we are looking into. Concurrently with this, so we saw our first few models explode. So we thought maybe if we implemented the full 3 PDEs with normalized parameters, we could come to maybe some more definite results about what terms are exploding, what terms are causing this, and maybe we can look at this behavior and change the simplified model to better look at these parameters. But then we also found that this model was also producing trivial solutions where everything would decay to zero, the magnetic moment density and the velocity across the board. So we're working through these problems while trying to keep model integrity. Some techniques that are being used for this are we're trying to increase the degree of refinement for a model. We are manually shifting diffusion terms, especially for the full 3 PDE implementation. It's decaying, so perhaps it's just something with the diffusion. We're changing initialization. So initially I was starting at 0 and it would grow, and because it's imploding, perhaps it's just overshooting some set parameter and that's causing it to implode. So maybe try to initializing it closer to what that could potentially be might help the stability of this model. And then also switching over to an HPC, so high performance computing for runtime. This would typically take an entire day to run 1 simulation a second, and we want to run this for potentially minutes. So HPC drastically improved this runtime. But this is a more recent behavior, so it took a fairly long time to get my first few models running. So for the first few cases, to show some of the results we have been getting, this is primarily just fluid dynamics implemented with little magnetic forcing. And we can see here that the model is becoming rapidly numerically unstable over time. It starts out very, very, very slow, and then at the end, it rapidly decrease, and then this will eventually cause it to implode. Another case that we ran, so we introduced the magnetic forcing. You can see uncontrolled growth, and this the previous one lasted around 10 simulation seconds, and this one only lasted 4, so we see a very reduced time scale for this. Second, this is basically the same as the previous case, but you can see the density grow at the very end, so perhaps it's some clustering in the density within the model that is causing this instability. Then for the full 3 PDE implementation, just to visualize this, we see a rapid decay within the magnetic moment density. This is the second one, and the velocity, which is just causes the entire model to decay and go to 0, something trivial. So new methods of validation, I was trying to look at the previous literature, trying to attain what they achieved, but there are other methods to validate what my model is doing. And one of these methods is just introduce a CFD model. So we set up a periodic case with an initial cell count of 128 times 128 grid size, which is extremely coarse, but it gives us something to work with, something that we can refine further, something to run very quick cases on within ANSYS. The idea of this is ANSYS Fluent, the MHD model within ANSYS Fluent cannot solve high frequency cases. So potentially we could implement a more easier behavior for this MHD model, compare that with the Python model that we have. And then if this seems promising, if these results are lining up and we can move forward with this, potentially we could implement a UDF or a more frequency-based module within ANSYS to account for this periodic behavior. So in terms of our next steps overall, we want to continue to establish this model until we see our expected behavior from the literature or from the CFD model. We want to continue this validation through our CFD model. And then finally, once this model is fully established, we want to optimize characteristics like the advection. This is one of the ones that we want to observe. Then particle formation and clustering, particularly the 3 ones I showed you before with bands, vortices, and the normal random swarms, fluctuations, those types of behaviors. So in conclusion, I went over the problem we're actually trying to address with biomed applications, the scope of this research, so establish the dynamics, Python model, and CFD validation, my objectives with different parameters, observing those effects, the actual equations being used within this research, our current results and the current results from literature, and then our next steps. Here's some references if you'd like to look into those equations and those results. Thank you. Do you have any questions?